Right, I'll be talking about some joint work with Martino Lupini. This work is not that new, it's from a few years ago, but we have revisited it, and we are actually now working on some number of edits and improvements of some results. I mean, the main results are the same, but presentation and some things that come much clearer now. And I thought it would be a good topic to talk about in this workshop. So let me fix some objects throughout. So throughout, we fix a countable, discrete group gamma, and a standard Borel probability space X mu without atoms. There's only one of them. And if you want to fix ideas, you can just think that it's 0, 1 with a Lebesgue measure. But you should also keep in mind that there's many presentations of this space. For example, the Hilbert cube with its Lebesgue measure is also isomorphic to this. And other perhaps less expected things, if you take just the 2-point set 0, 1 to the integers with the product of the counting measure, that's also something like this. So the main focus of my talk is actions, so in ergodic theory. So let me just define right away the two main notions. They will stay up here on the top left. An action, say of gamma on X mu. This will be always implicit, but I always mean probability measure preserving. So we'll write it just in this definition, but not again. So this is already implicit in the notation. Gamma is assumed to preserve mu. So PMP action is, and it always acts by measurable bijections. So this is the category that we're working in. Is said to be, and there's two definitions. The first one is free if for every group element that is not the identity, the set of points that are fixed by that element, so this is equality, is 0. So up to discarding a null set, since the group is countable, we can assume that the action is actually free, has no fixed points. In ergodic, if the only invariant subsets that are measurable have either full or null or co-null. So if whenever E is Borel and gamma invariant, then, I'm sorry that this got so small, mu of E is either 0 or 1. So there are no subsystems in the suitable category. Okay, so I will, since it's Friday, the last talk, and we're all tired, I was intending to motivate the problems for some time, so give you like put them into context and give you a bit of introduction, and describe the results, and at the end, if I get time, also describe a sketch of the proofs and some particular cases. So let me start with the part of the introduction of the motivation of the problems. So this goes back to the very beginning of ergodic theory, where the very beginning people were interested in studying the long-term behavior of measurable dynamical systems. And so back then you see, for example, Birkhoff's recurrence theorem, or so Poincaré recurrence theorem, Birkhoff's ergodic theorem, von Neumann's ergodic theorem. So these are all results, if you look at the statements, that tell you what happens in the dynamical system when you let the time pass a lot. And on average, some things happen, or recurrence, or once this behavior was understood, or was understood well enough, the attention shifted to understanding when two systems are equivalent. So this is conjugacy. This brings us to the notion of conjugacy. So two actions, and this is exactly the notion that you would expect. I will just state it for the sake of completeness. So two actions, let's say, let's give them names. Actually, let's not give them names. So the group is the same, and we're acting in two different spaces. Our conjugate. If there exists a Borel isomorphism that intertwines the action, so such that if you map through F a group element acting on X, this is the same as G acting on F of X. This is for every G in gamma, and as usual for almost every X, but I will just write for every X in X. So this is conjugacy, and so already back at the time of, around the work of Chalmers, this is very clear that understanding when two systems are conjugate was very relevant. And actually, obtaining classification results in terms of conjugacy is rare. There are not so many. So let me just write that. So not so many positive results. So positive classification results. Except that there's a very bright spot given by Bernoulli shifts. Yeah. So except for. So let me tell you what they are. If you haven't seen them before. So you start with a base, let's say x mu. For this definition, the base doesn't have to be atomless. So let's say let's give it a different name actually. So let y nu be a standard probability space, Borel probability space. The group gamma is fixed. Define the Bernoulli shift with base y nu. So since gamma is fixed, I will not include it in the notation. So it's just beta y nu. It's an action of gamma on the infinite product of y nu indexed by the group gamma, which we think of functions from gamma to y. So this is just given by beta y nu on an element G. And now if your function from gamma to y, I will write it by psi, evaluated at H. Now this is psi of G inverse H. Okay, so this is really just permuting the copies of this infinite Cartesian product according to the group law. Gamma, you would do it on the left, could do it on the right. It gives you you don't have to take the inverse if you do it on the right, or you should not take the inverse if you do it on the right. But I will, for example, is this one the right one? So I'll tell you about a very famous question that was solved. I mean, you probably know this already, but this is a question of Chalmers. So let's say that we take gamma to be the integers, and we take now two different bases. One of the bases will be the 2-point space with the counting measure, like the normalized counting measure, and the 3-point space with the normalized counting measure. So R, and I take the same. R, so let's just write it like this. So I'll just put here what the weights are. So 1/2 and 1/2. So this is telling you what the measure on this space is. So this gives you a Bernoulli shift. And the same for 3 points. 1/3, 1/3, 1/3. Sorry, and Z acting here. So both Bernoulli shifts, are they conjugate? This is actually very challenging. Now we know that the answer is no. They have different entropy. And so this is Kolmogorov Sinai, who introduced this entropy and proved that they are. It's actually quite difficult to compute the entropy of these Bernoulli shifts. But upper bounds are easy to, or lower bounds are easy to construct, but the actual value is difficult. So it's not a trivial statement. I mean, once you have the invariant to actually compute in these cases, is, yeah. And this was actually groundbreaking at the time. But even more surprising was a theorem of Ornstein that tells you that if you have two Bernoulli shifts of the integers, so now the bases can be completely different. There have to be these two specific ones. If you have any Bernoulli shift, any two Bernoulli shifts, if they have the same entropy, then they are necessarily conjugate. So the entropy is not just an invariant of conjugacy, but for the class of Bernoulli shifts, it is a complete invariant. Notice that once you fix the space to have 2 points, you can have different weights here. So even if you just restrict to finite bases, this is a very surprising result. So Ornstein proved in 1970 that so entropy is a complete invariant for conjugacy of Z Bernoulli shifts. So Ornstein. So this was generalized greatly, and let me just add some names here. So Ornstein and Weiss did this for all amenable groups. Then, and there's a series of works. Lewis Bowen, for example, did it for free groups. Then Kerr, Lee, and Seward completed the picture for the Sophic case. And the statement is that Bernoulli shifts of Sophic groups are classified by entropy. So this is a bit subtle, and I honestly do not know exactly the answer. I think there are subtleties there. So I think you have to fix a system, and then if you exactly. You fix the system for the group, and now you consider two Bernoulli shifts. And so I think that, I mean, the theorem is still a classification theorem, but I think there's a subtlety there with Sophic entropy and how much and to what extent it depends on the. So okay, now you say this, it agrees with the Shannon entropy of the base if the base is purely atomic. So in cases where the base is a finite set, so purely atomic like this, it is the entropy of the space without the action. So in that case, it does not depend on the. I'm not sure in general. David, you want to? You were raising your hand.
Maybe you're speaking specifically about Bernoulli shifts, but in general, like the scope of the population definitely can change the value of density.
Yes. Yes. I mean, I think for Bernoulli shifts, it really does give you the Shannon entropy of the base. Of course, in general, you don't have a base to talk about. So, yeah. But I'm not an expert in Sophic groups, and I'm also not going to define them because it's not really central to what I'm saying. But Sophic groups are, I mean, there's not an example of a discrete group which is not Sophic, so this really covers. Right, linear groups, residually finite groups, etc. Right, so here's a question.
There are examples of groups that we don't know are Sophic. What do you mean to say that we don't know any example of non-Sophic?
Okay, that's not what I said. Perhaps I misspoke. Yeah. There's no group known not to be Sophic. Thanks. Right, so this is also a question of Chalmers. I mean, if you know some of these names, you realize that some of these results are very recent. This one is from the 70, 80s, and this is really much more recent. But this question of Chalmers was stated around the time that Ornstein proved his version for the integers. And the question, which is really the motivation for this talk and this work, is a bit vague. I will state it how he did it, how he stated it, and then I will reinterpret it in the context of the scripted set theory. Determine, or how can one? Is there a method? Perhaps an explicit method to determine if two transformations are conjugate to actions. So this is in his from his lecture notes on ergodic theory. I mean, he also wrote there. I mean, the question is vague, but what he had in mind, he explained, is this result of Ornstein, which is so beautiful. You just compute the entropy of the dynamical system. So you just compare the numbers, and if they're the same, they're conjugate. If not, not. So this is what he had in mind with a method. Of course, we're mathematicians who want to give this question a rigorous interpretation, because if we want to answer a question, we have to determine what the question is. And there's, of course, many ways that you can interpret this. One way is in the context of computational theory. Is it called like this? I mean, you can interpret this method as meaning a recursive algorithm. So for example, this would be a Turing machine with a finite list of instructions that if you give it as an input to actions, and with this finite set of instructions, at some point it gives you the outcome, whether they are conjugate or not. So this uses, I mean, inherently finite amount of information, and this is really very rigid. You can relax this and, for example, ask whether there's a method that uses a countable amount of information, and with the same idea, right? So you give it two actions, and after countably many steps, possibly use a transfinite induction, tells you whether the actions are conjugate or not. And this is the interpretation that we're going to take. Can be best explained in the context of descriptive set theory. That Peter was already hinting at this. I will review it anyway, but this is the notion of a Borel equivalence relation. So let's put this into context. So perhaps parentheses. So let's give it a name. Z be a Polish space or complete metric space. Let's say compact. Metric space. Separable complete. Sorry for this. And let's say twiddle be an equivalence relation, which I think of a subset of the product, consisting of the pairs that are equivalent. We say that the equivalence relation is Borel. If it is a subset, a Borel subset of the product. Of X, Z cross Z. Okay, and then the reformulation of the question of Chalmers in our context was given by Kekris something like 20 years ago, and it asks, is the relation of conjugacy, they did not write a symbol here, but this is what this is conjugacy for free ergodic actions Borel. I have to explain to you how you regard the set of free and ergodic actions on a standard Borel probability space as a separable complete metric space, but this is not so difficult. So this is in parentheses. The set F E gamma x mu free ergodic actions of gamma on x mu is a subset of the product, Cartesian product indexed by gamma of the automorphism group of x mu. Yeah. So this is a Polish topology. You can take the product topology there, and you can see. I mean, the definition is right there. You can see that these conditions are. They give you a Borel subset. I mean, this subset, using the definition, you see that in the topology that I described, this is a Borel subset, union, intersection, closed, and conditions, and so on. So is a Borel subset. I think it's closed, but this is not the point anyway. Okay, so we know how to interpret Chalmers' question is in the setting of descriptive set theory. What about answers? So the first answer came actually in 2011. So this is Foreman, Rudolph, and Weiss. And so before I tell you what the answer is, observe that although this is just one question, there's really one question for every group. Yeah, so the space is fixed, but the group is not. So for ergodic actions of gamma. So for every group, there's a question. They answer the question for the integers. For the integers, the answer is no. This was, yeah, very well received, very important publication, and very surprising, perhaps, if you wish. Of course, once you know that this fails for the integers, you have essentially no hope that it will work for any other group, except for maybe finite groups of very silly things. The next result in this direction came later. I forget exactly the year, maybe 13 or something. So this is of Epstein, who's now called Moroz. So she married. This is her last name now. I think the paper is published under her old last name. That's why I write it like this. Turnquist. So they proved that if Fn is a normal subgroup of gamma, so this is exactly very non-amenable, right? So this is a non-amenable group that contains a free group as a normal subgroup, then the answer is also no. Running out of space, perhaps let me tell you the last result that was. This result I will say stated with lowercase t because it's not out, and this is really private communication. So when we posted this a few years later, Benjamin Weiss emailed us, and he told us that together with Foreman, they can show that if gamma is amenable and projects, so it has a surjective homomorphism to the integers, then the answer is no. Okay, so this of course doesn't cover all non-amenable groups, but it covers not all amenable groups, covers quite a lot of them. They did not write it up, so that's, okay, lowercase t because it's, don't quote me on this, just want to refer to them. And so one of the things that I want to present here is the fact that we could answer this question for all non-amenable groups. Of course, given all of these results, the answer should not be surprising. The answer is also no. But okay, yeah, proving it is not always as easy as guessing what the answer is. So with Martino, we proved that if gamma is not amenable, then the answer is no. So this equivalence relation seems to essentially never be ORL, except in the trivial case of a finite group. So later will come a sketch in the case that the group contains a free group. But before we go there, I want to talk about the orbit equivalence problem. So this question of Chalmers, this is sometimes referred to as the conjugacy problem in ergodic theory. But there's another equivalence relation that is also very interesting particularly for operator algebraists. So orbit equivalence. And the reason why you might consider this one is that although conjugacy is very nice and very natural, it's sometimes too rigid. So for example, if you have a transformation, so an action of the integers, you look at the one given by the inverse transformation. So, if t is a transformation, you let the integers act by powers of t, so n goes to t to the n, but now let it act by the opposite power, so n goes to t to the minus n, essentially replacing t for t inverse. For all practical purposes, you would like them to be identified. They are very, very similar, clearly, right? Generically, they are not conjugate. So for most free ergodic transformations, they are not, most free ergodic transformations are not conjugate to their inverses. But there should be, there is a notion under which they are always equivalent, and this is, for example, orbit equivalence. So this just means that I have the same orbits. Let me define it properly. So here the groups don't have to be the same. So gamma and so R orbit equivalent if there is a Borel isomorphism of the spaces such that, well, it sends orbits to orbits. And again, for almost every x, but you discard a null set and it's just for every x. This equivalence relation is a bit closer to the hearts of operator algebraists because it admits a phenomenon algebraic characterization. Let me just state it. These are the only phenomenon algebras that would appear in the talk, actually. So gamma acting on x mu is orbit equivalent to lambda acting on y nu, and I have to at least assume that they are free. I think ergodicity is not needed, but I'm assuming these two things anyway, everywhere. If and only if there is an isomorphism between the von Neumann cross products, so I run out of space, that maps the L infinity copy of the first one into the, or onto the L infinity of the other one. So L infinity of x goes onto L infinity of y. Okay. So again, you may ask the question, is orbit equivalence for free ergodic actions of gamma a Borel equivalence relation? So, and this is what Kekris also asked in the same book. Is orbit equivalence Borel? And again, I always mean for free ergodic actions of this previously specified group gamma. So this for every group one question here. Perhaps you already know, and I should have maybe mentioned this even before I stated the question, the amenable case was resolved very early on. In fact, as soon as this notion was introduced, it was proved that if you have two free ergodic actions of the integers, so this is Dye's theorem, for the integers, free ergodic actions are always orbit equivalent. So, and this was generalized by different people, but Kohn, Feldman, and Weiss, for example, Dye, Kohn, Feldman, Weiss, and they proved that if you have two amenable groups, and they don't have to be the same group as long as they're infinite, if you have two infinite amenable groups and two arbitrary free ergodic actions of each of them, so one of each of them, then these actions are always orbit equivalent. So said in a different way, now specializing to one group, if you have one amenable group, any two free ergodic actions of this group are orbit equivalent. So any two free ergodic actions of an amenable group are orbit equivalent. So this means that this equivalence relation, when the group is amenable, has a unique class. And if it has a unique class, it's trivially Borel, right? It's a whole product space. So in this setting, this equivalence relation is always Borel. The question really only makes sense or is only interesting for non-amenable groups. And what is known for non-amenable groups, right? So then there's a result of Hjorth that if gamma is non-amenable and has property T, so I'm excluding finite groups for this, then orbit equivalence is not Borel. And the other result that was also known is, in the same context that Epstein and Turnquist proved the result for conjugacy, they also prove it for orbit equivalence. So if gamma contains a normal subgroup isomorphic to a free group, then also not Borel. Okay, and then the result that we proved with Martino we complete, actually in the case of orbit equivalence, we indeed completed the picture because the amenable case is very well understood, it's always Borel. In the non-amenable case, the answer is always no.
So this last theorem, this is the one that uses some construction of Johanna, right?
Yes, of course, exactly. Yeah, specifically if you want to do it for orbit equivalence. If you want to do it for conjugacy, you don't need this co-induction, but you need some rigidity of exactly the action that you take on T2. Perhaps I will come back to this, or I will go into that. So Gardella Lupin, if gamma is not amenable, then conjugacy, orbit equivalence is not Borel. Okay, so for orbit equivalence, it's really completes the picture, and it gives you this dichotomy. Gamma is amenable if and only if orbit equivalence has a unique equivalence class, namely all actions are equivalent, and as soon as you're not amenable, well, then you have at least two, because this is what one tells you, but as soon as you have at least two, you have such weird and oddly behaved equivalence classes that the equivalence relation is not Borel. So there's nothing in the middle. There's nothing, for example, countably many classes with a Borel equivalence relation. So this is a dichotomy. Before I move on to tell you more about the details or what goes into the proof, yeah? Oh yeah, sorry.
So I'm sorry for the repetition, but can you please explain to me again what is the notation OE?
Yeah, sorry, it means orbit equivalent.
No, but like, when you say, is that Borel, what exactly do you mean? Like when you say, if gamma is not amenable, then OE is not Borel. What exactly do you mean?
Right. So there is a notion of what it means for an equivalence relation on a Polish space to be Borel.
Yeah. No, but like.
And then what's the question?
In your main theorem, you're saying for all actions of for all, it just says if gamma is not amenable, then OE is not Borel. So
OE for gamma actions.
if you ask me what is the space, what's the Polish space? You said it before.
Yeah, it's the free ergodic actions. I think it might be still, yeah. If I'm lucky, yeah. So this is the space where I consider the equivalence relation tilde OE. If you want to be very pedantic, is perhaps not the word, but there should be a gamma also in this relation, right? Because it's one for every group.
Right, yeah, I know.
And this is the space where I take the equivalence relation.
Yeah. Sorry for the repetition. That's why I said in the beginning.
No, it's okay. I was just, didn't understand where the omission was there. Right, and before I move on, I wanted to say that there has been a lot of work done for a related question, which is not about the complexity of the equivalence relation, but about the number of equivalence classes. So a lot of, I'll just write it. So this is a combination of results or accumulation of results of Popa, Gaboriau, Popa, and Johanna and Epstein. So what they show, actually, this is what I'm going to say. This is Epstein's result, but it really builds on everything else. If gamma is not amenable, then orbit equivalence has uncountably many classes. Uncountably classes, many. Formally, neither this result implies this one, nor does this one imply that one. But the way that we prove it does, in particular, show that there's also uncountably many classes. So although it doesn't follow formally from the statement, it really does follow from the actual way in which we show that this is not Borel. Because we obtain a Borel reduction, this is what Peter was talking about, from abelian groups to free ergodic actions. And of course, there's uncountably many abelian groups. This gives you uncountably many actions that are they actually realize the fact that the equivalence relation is not Borel. But really, very big amount of work has been went into proving that, and perhaps not surprisingly, we also take advantage of the things that they developed to prove our result. Right. Any questions? So what I want to do in the 20 minutes that I have is tell you a bit of how we prove this, and I cannot get into many details, but in the case that the group contains F2, maybe I can even almost sketch so arguments. So Peter was talking about Borel reductions. So let me just recall. If, and we'll use this notation, if E is an equivalence relation on a space Z, and F is another equivalence relation on a space, let's say W, then a Borel reduction from E to F is a Borel map from the space where E is an equivalence relation to the space where F is, which induces an injection of the quotients. Okay, so two elements in the target, two elements here are equivalent if and only if the images here are equivalent. This is precisely stating injectivity. What we will need is a weakening of this, so a countable to one Borel reduction or Borel homomorphism from E to F is a Borel map, just the same thing, from the first one to the one which you reduce it, such that, which induces not an injection necessarily, but a countable to one map in the quotient. So countable to one. It is perhaps well known and certainly not very difficult to see that if you have a Borel reduction from a non-Borel equivalence relation into another one, then that other one cannot be Borel. This is the way to think about Borel reductions is in the setting of that one, for example, that F is at least as complicated as E. So if E is very wild, then F is going to be very wild as well. So in the context of the Borel reduction, if E is not Borel, then F is also not Borel. And we're going to use a version of this for countable to one reduction, specifically for isomorphism of abelian groups, which was proved by Turnquist, or Epstein and Turnquist. Let me add notation to this. Let's say E. So this will be Borel reduction, and I will add an n here for countable to one. So if isomorphism of abelian groups, and this is the notation I want to use for that, isomorphism of abelian groups, satisfies this, has a countable to one reduction to another equivalence relation, say E, then E is not Borel. Yeah, behind this is also the fact, of course, that this equivalence relation is not Borel, and it's so not Borel that even under countable to one reductions preserves non-Borelness. So what we do, and this is the actual theorem that we prove, we show that there is a Borel map or assignment. Let's call it capital theta from abelian groups to free ergodic actions of gamma on the atomless standard probability space. Here, forgot to say, but this is gamma is non-available. Such that, so two conditions, if you have two abelian groups that are isomorphic, A and A prime, then the actions are conjugate. So theta A, actually this is locus theta. Theta A is conjugate to theta A prime. And if curly A is a collection of abelian groups, pairwise non-isomorphic, and all of them give you the same orbit equivalence class, then A is countable. It sounds like a mouthful, but what you have to take out of this, or what this implies, is that both conjugacy and orbit equivalence admit Borel reductions, accountable to one Borel reductions from isomorphism of abelian groups, and therefore they're not Borel. So once you prove this by the result of Epson and Turquoise, the result is proved, and then also this result about the number of classes follows from it, because you index them by abelian groups basically.
You basically have some sort of translation of countable groups, right?
Yeah. Oh. No. No. Yeah, but I'm not going to show you enough of the proof that because no, it's not clear at all. Not to me, at least in this moment, but perhaps it's interesting. The thing is, the map is Borel, but it's not canonical. I mean, there are choices involved, and but the choices. No. But I mean, it requires, for example, fixing beforehand a subgroup of SL2Z, which is free. And then if there's more than one, you fix one, but you do it for one. But then, in principle, the relation that you get on abelian groups may depend on this, I think. Yeah. Then it's not it's not well defined or not a very intrinsic. Yeah. Yeah. So I wanted to avoid giving too technical definitions, or definitions that are too technical, but let me give a pseudo definition. This so suppose you have a nested triple of groups like this, be discrete groups, and let theta be an action of the big one on some space. So I will assume that you have seen some version of one cohomology for actions. This is constructed from one cocycles for the action, modulo the coboundaries. There is, and I'm not going to define it, but there is a cohomology. So this is a notation, it's H, upper one, this is one cohomology, so far so good. Delta trivial or delta invariant, lambda relative and weak for the action theta. I really, you don't want me to define it, I also don't want to define it, don't worry. So This stands for the fact that the cocycles that you use are trivial on delta, and the elements of delta for the group that when it's acting fix the unitaries coming from the cocycle when restricted to lambda. The weak part is that when you what is the definition of coboundary? So you identify things that are differ by a coboundary up to scalars. So this amounts to allowing for a scalar when you say that something is a coboundary, or two things differ by a coboundary. It's up to scalars, one scalar for all the group elements. Really, trust me, this is not really central. Since I'm using it, I at least want to tell you what the notation is, but it's an invariant of conjugacy. And the important result for this, of course, I'm not telling you what the definition is, so how meaningful is the result. You will see later that you can complete the proof of the main theorem just formally from the things that I'm writing down, if you accept the theorem that I want to state now. In some sense, it's a pseudo proof, but I think it's still worth it. This is a superrigidity theorem. Cocycle superrigidity a la Popper. So this is an extension of Popper's result for pairs of groups with property T. And I will state it in the case that I care about. So if delta is normal in lambda, infinite index, and the quotient has property T, then for the Bernoulli shift of gamma on x mu, so here's a quotient times, and now again gamma. So this is just a product of the Bernoulli shift. So you act here canonically, and you act here canonically. We have that the delta invariant lambda relative weak one cohomology of beta of this guy is trivial. Okay. Gamma is the big group. Yeah. So you have a big group that contains two, a subgroup and then a subgroup of that. Right. Right. So this is true, and if it was just one cohomology without any of these decorations, this would tell you that if two actions are orbit equivalent, then they are actually conjugate. So this is really a superrigidity result. Orbit equivalence implies conjugacy. This is an extremely rare phenomenon, and this is the kind of things that superrigidity theory gives you. So here's a construction. Yes, but this is, I don't want to sell this as the main result, because this is really okay. You have to adapt, and it takes a lot of work, but you have to adapt the things that Popper did to a more general setting. That is just on your particular case here, but sure, a lot of work goes into this. It's not the main innovation, I would not say. So the construction of theta in the case that there's a free group instead of gamma. So let's do it then. So when we have a free group instead of gamma, we can take the free group to be the intermediate group, and now we're essentially free to choose our delta. And what we choose, is a subgroup of Fn of infinite index whose quotient has property T. This we can always do. So fix delta normal in Fn with infinite index, and the quotient has property T. So now, so I want to construct theta. So what I have to do is start with a abelian group, call it A, and then set G to be the dual group. This is a compact group. I endow it with the hard measure and said, just to abbreviate, M is L infinity of G. Now consider M to the same tensors as we have for the Bernoulli shift, gamma mod delta tensor. This is always for Norman tensor products. M to the gamma. So here we can act by the Bernoulli shift. So this is gamma acting here, but we can also act by G. So G, remember M is L infinity of G. G acts here by left translation, for example. So G acts on each tensorial factor individually without mixing them. It acts the same in each factor. So I would just say left translation, but it means left translation everywhere in each copy of M. These two actions commute because this one acts the same in every tensor factor. Notice that beta does not depend on A, because this does not depend on A, but this one does depend on A. All right, so the dependence on A is on the right-hand side. Since they commute, beta restricts to an action on the fixed point algebra of the G action. And this one I will call theta. And M sub A is the fixed point algebra of this guy. Okay, if two actions commute, then one restricts to the fixed point algebra of the other one. It's always true. And okay, so the notation already indicates that this is my theta. Well, one can show it's clear that if A is isomorphic to A prime, then the actions are conjugate. There were no choices made here. And one thing that one shows, this is not difficult, but I probably don't have enough time, is that the delta invariant lambda relative weak one cohomology of theta A is isomorphic to A. And for this, one uses the superrigidity result. And I will tell you very briefly how you use it. If you have, so take an element of this one cohomology group for theta A. Take a representative, so it's a cocycle for theta A, regarded as a cocycle for the larger action for the beta. Theta A is a restriction of beta, but you can always regard a cocycle for theta A as a cocycle for beta. There it is trivial, so you trivialize it upstairs. And this weak part, I told you before about scalars, this will give you actually a character of G, which is an element of A. Okay, this. Yeah.
MA is some L-activity or something, right? You want the underlying space there?
Yes, right. So, yeah. Yes. Yeah, because all of this is commutative, clearly, right? So MX commutative.
So MA is a computed phenomenon algebra, and you want to take the underlying space.
Exactly. So MA is L infinity of XA mu A. And this one is going to be atomless because everything else, because everything else is atomless. So it's really X mu again up to identifications. Okay, this doesn't quite tell you, in some sense it tells you if and only if here. So this really is a Borel reduction. If on the nose, this is really a Borel reduction from isomorphism of abelian groups to conjugacy of free ergodic actions. So if you could complete the proof that the things that I'm not doing, this tells you that conjugacy is not Borel if you contain F2. Proving this takes a little bit more work, and actually this is not the construction that you need to use if you want to prove 2. So if you want to show the result for orbit equivalence, you have to, as Siri was saying, combine this with some co-induction for the rigid action of F2 on the torus. I want to skip that part. The thing that I want to tell you perhaps in 1 minute is how to go from groups that contain F2, which is what I assumed somewhere here, groups that contain a free group, to arbitrary non-amenable groups, because I think actually this is extremely interesting. And so surely all of you know, there are non-amenable groups that don't contain F2, although this was open for some time. There's many examples of this. There is a nice result of Gaboriau and Lyons that says that although a non-amenable group may not contain F2, it always contains it measurably in a suitable sense. So if gamma non-amenable, then F2 is actually contained. This is not a mathematical term. I will tell you in a second what it actually means. Measurably contained in gamma. And what I actually mean by this is that you look at the Bernoulli shift of gamma on the standard probability space, call it beta. So let's say beta is gamma acting on x mu to the gamma. This is given, so there exists a free ergodic action of F2 on x mu to this power, so this on the same space, both things act on the same space theta, such that the orbits of this action are almost all of them contained in the orbits of the other action. So up to considering measurable dynamical systems and up to the orbit equivalence relations, F2 is containing gamma. Okay, so this, of course, does not give you an inclusion of F2 and gamma at all, certainly not as a subgroup, but we're interpreting everything as equivalence relations and even better as étale groupoids, Borel étale groupoids. You can actually carry out a co-induction construction that allows you to go from actions of F2 to actions of gamma. And this is what you use to complete the picture in the case that gamma may not contain F2. Okay, that was all I wanted to say, so thank you for your attention.